So the second part, okay, we probably use too many minutes for the first part, but I guess we'll go over the other 6 parts faster. Okay, so for this abstraction and specification process, I'll use this visibility as one example. So the goal is the visibility of a function should match the API spec in programmer's design. When you have your design doc, you figure out what should be public, what should be hidden, and then you try to say that I'm sure people know these 2 files, that the Android MK. I mean, we are all practitioners, so I guess we are like, oh, this is an Android tree anyway. Okay, so the key is if for a particular component you want hidden visibility, you want to reduce the size. Okay, then you can set this visibility as hidden, and then for those functions that are public, that are intended as a public API, then you append this attribute visibility public next to the function declaration, and then you remake. So if you are very familiar with your components, you know which part is public, then you probably don't need to do much work here. You don't need to do a lot of iterative things. When I was first doing the open code, because I'm now very familiar with open code, I just iteratively going through those, and then we can say, okay, we find all the remaining functions that should be made public. So this way, it gives a lot of size benefits. So now you can use smaller footprint on your ROM. The key savings is actually from garbage collecting away all the sections. Because in Android today, I think people know that each function is a section. So when this is a default in the default toolchain option, -f function section. So each function has its own section in the linker terminology, and then if those hidden functions are not used, then you don't need to, they are not exposed. Before, today the default is everything is public, and then so even though this function is not used in this file, you cannot recycle those. But now you know you can garbage collect, you can recycle those, and so the whole function body can go away. That's the whole, basically that section containing this function will be removed. So that's why we can get double-digit size savings on this. Okay. So the third thing we try is to use systematic parameter setting. I think those configurations are key drivers in performance and size optimizations. So for Android tree, we want to find the best parameters, and here we use compiler options and the parameters as case study. But I guess this can be used in other places as well. For example, TI has this code composer studio, and so as your code base is evolving, for example, people checking new patches to Android trees throughout the week, and every Friday before you go home, you can start this parameter space exploration, and then by Monday morning when you come back to work, the best options, so the best parameters for your newest code base should be there already. So TI Code Composer Studio has this, and we just try to do some parts for the Android as well. So this just a detail on this parameter search, because jumping ahead, there are tons of operations you can search, and then this is the default options today, and then just by inlining alone we can find much better values. For example, the parameter for this should be 62 and so on. So how do we search this number. How do we get those numbers? It's an exponential problem. So we can use genetic algorithm they will utilize this crossover and the mutation to find the best options quickly. So with this kind of directed genetic algorithm, we can get a good trade-off between performance and size. So in this case, for example, the native system image parts, all the system libraries originally is about 23 megabytes, 23.9, and then by using newest Toolchain, we can get 23 megabytes, about 800 kilobytes savings. And then with the inline options, we can further remove about 750 kilobytes. So this is about 7% savings from the Toolchain today. So this gives us savings furthermore. And the fourth strategy I'm going to cover is this profile guided optimization. So the key thing is that if you need to spare temp 1 or temp 2 before temp 3, say if you run out of registers in your ARM processor, how do you know which one you should spare? So if you know this is a hard path, if this in your program, if you know this is more executed, then you can just spare. You need to spare temp 2 because this won't affect the common path more. And this path, you need to spare this register to memory and load them back from the memory later on. But this one won't affect the common path. So with this illustration, then when you try to squeeze more size or improve performance, then you can do these 3 steps. Basically, for FDO, you need to do this build and profile and then use. So this is the flex you can use today already. So the key thing is you find representative inputs for the second step, and then the instrumentation is slower, but it's okay. It's not the final binary, and also Android is not that timing sensitive. You won't introduce data race during the instrumentation. So you can believe the instrumentation data and then use those data for optimization later on. Okay, then I found that I really need to speed up. So basically the key is you can get about 7% improvements, and then you can also tune this flag in your Toolchain today, the hot basic block counts fraction. So you can make sure your hotness is global hotness, because sometimes if local function inside local function, this basic block is very hot, it doesn't mean it's globally very hot. So you can further get much more improvement on this. And the fifth part is this IPO interprocedure optimization. If, for example, if these 2 scopes are merged, the computation, the expression here is 0 because I minus j plus j minus I is 0. So we try to enlarge the scope and get better improvement. And then there's a traditional IPO. That's monolithic and serial. So we try to do this lightweight IPO. This is just done before I fly back here early yesterday morning. So you can try this and then let us know whether you can get a lot of improvement. At least so far we see quite a bit of improvement by enlarging the scope. So in the interest of time, here you can just see a lot of improvement. And here I explain how you can enable this using the LiPo. And we just got, like I said, we just got this version working. So you can do this later on. And I also for the 6th one, identical comp date forwarding. It's a better name because it has nothing to do with comp dates. So I tend to think it as identical code forwarding. Basically, identical you find identical functions and merge them at link time, and then you trigger with this option, and it's already in Google's Gold, and it does about 5% improvement. And when we look at the Android code, it's also about 5 to 7% improvement. Like Skia, for example, the 2D graphics, we see a lot of redundancy in the generated code. So this can improve a lot. And the last one is about optimizing memory management. So Delphi uses malloc to manage each heap. So you can call mspace carrot or mspace free, and